Here are two more examples involving Parseval's theorem. The first is you're given a voltage signal, and it's one that's got a DC component, and it's got a couple of harmonics. Now, by now, although you can see that this particular example is using a sum of cosines, so you can just see what those Fourier series components are. I could have just as well given you a square wave or a triangle wave or some other wave, and you do the Fourier series breakdown for a certain number of harmonics to get it into a format that looks like this. Now the question is, given this waveform, I want you to find its RMS voltage. Remember, that's the DC equivalent, so that if you put that DC RMS value as a voltage into a light bulb, it would light just as brightly as this complicated changing thing. So there's two methods to do that. The first is one that we talked about a long time ago, back in circuits 2. And that method says to take it uses what the definition of RMS value is, which is it's the square root of the mean, and we said the mean is 1 over time period times the integral over any time period of that square of that voltage dt. And the square of the voltage is the square, so it's the root mean squared. This is computationally really, really painful. And that's because this voltage, when you square this, you're going to have all these cross products. Now, some of the cross products will simplify, but you still end up with 6 different things you've got to take integrals of. Not fun. So instead, if you were to see this on an exam, you would use Parseval's theorem. And Parseval's theorem says that you know that the power, the average power, is VRMS squared. And you know that's also equal to the sum of the powers of each of the frequencies. So that's the DC power plus 1/2 times the sum over all those harmonics of all those other upper level harmonic powers squared. We can just read this out for this example. That's 3 squared plus 1/2 of, let's see, the first value we said is 2. And the second value we said is -1. And so add all those guys up and you get 9 plus 1/2 of, let's see, 4 plus 1 is 5. And so the whole thing comes out to be 11.5. Of course, that's the square of the RMS value. So the RMS is the square root of that, and the square root of 11.5 is about 3.39. And the units of that are volts RMS. Wow. A whole lot easier to do that than 6 painful integrals. Here's another example. This is a very real world example, and it has to do with a power company. Now, power companies understandably like to have control of their power grid. The federal government, meanwhile, wants to encourage understandably wants to encourage alternative energy sources being used. So the federal government tells power companies that they have to agree to buy back power produced by small producers of alternative energy source. But the power company says, how do we know that these... The power company says, hey, I've got this beautiful 60 hertz sine wave of voltage on my system. How do I know that these small producers aren't going to give me something that looks like this, that's painful? And so the power companies say, we will buy your power back, but only if you promise us, if you prove to us that it is 99% spectrally pure, meaning it's 99% sine wave and 1% or less all this other schmutz. So how do you come up with a test that proves that your signal, that your power source, is 99% a pure sine wave? Well, the test that you devise is that the power from your 60 hertz portion divided by your total power, you want to prove that that is at least, that is greater than or equal to 0.99. So how do you prove this? Using Parseval's theorem, the power at 60 hertz is equal to 1/2 times your first Fourier series component. Your total power is equal to your RMS squared value. And that's what you want to prove is greater than or equal to 0.99% to force the power companies to buy your power back on the power grid. Again, something definitive and unambiguous.